Hello everyone, and welcome to the video for section 8.5 on the determinant of a square matrix. Skill objectives for this particular video are: number 1, find the determinant of a 2 by 2 matrix. Number 2, find the determinant of a n by n matrix. So we're going to try to generalize that process, and then we're going to use Cramer's rule to solve a square system of linear equations. The conceptual objectives on this one. 1 is the derivation of Cramer's rule. Where does it come from? Number 2, understand the consequences of when the determinant is 0. And number 3, understand Cramer's rule can only find unique solutions. First, I want you to recall something that we talked about last time in terms of working with the determinant. And that was that when we had a 2 by 2 matrix, last time we dealt with the inverse, and we had that if matrix A was this, A, B, C, D, then A inverse is 1 over AD minus BC times this, D, the opposite of B, opposite of C, A. A and D switch places, B and C have same signs. But really the issue comes in on this one is what happens when the inverse doesn't exist. And really the inverse doesn't exist. The only way the inverse doesn't exist is when this thing right there is equal to 0. When AD minus BC equals 0, we know the inverse doesn't exist. So really what we want to do is we can use that fact to help us determine if a matrix has an inverse. And that, what you see right there, is what we call the determinant of a 2 by 2 matrix. So by our definition here, we're going to let A be the matrix A, B, C, D. Then the determinant of A is given by this notation here, determinant of A, or what will look like an absolute value sign around the matrix, or written like that, where the brackets are replaced with what looks like an absolute value sign, and that is going to be AD minus BC. So for example, I have two matrices here that I want to find the determinant of. Well, the determinant of this first matrix right here, A is, remember, it's AD minus BC. So A is -2, D is -2. So it's going to be -2 times -2 minus B and C is 1 and 3. Minus 1 times 3, which would be 4 minus 3. So in this case, the determinant of this matrix is equal to 1. What I'd like you to do is pause the video. I'd like you to find the determinant of that matrix, of the matrix 5, 4, -2, 5, -5. So pause the video, find that determinant, and once you have it done, come on back, we'll take a look at it. Okay, welcome back. So in this case, the determinant on that one, remember, is going to be A times D. Well, in that case, A times D is going to be -25 minus B and C is 4 times -2, which will be -8. So -25 minus a -8, which is -25 plus 8. So in that case, that determinant came out to be -17. So the determinant of that matrix is -17. Now what we got to do is take a look at how do we go about finding the determinant by hand of a matrix that's not 2 by 2, because we have a nice formula for a 2 by 2. And I wish that I could tell you we have a very nice formula for calculating the determinant of a 3 by 3, 4 by 4 of any matrix, of an n by n. What I'm going to show you here is a way that we can go through and calculate the determinant of a matrix, of any square matrix, regardless of size. We have a nice formula for 2 by 2, and there actually is something else we can do in terms of 3 by 3, which I can show you in class. But in general, this is what you're going to see here is really how we go through and find a determinant of something bigger than a 2 by 2 by hand. And what we're going to do is we got to go through and get we got to go and deal with this. We're going to deal with an expansion by cofactors. And to deal with that, we have to define two terms, a minor and a cofactor. So what happens here A is going to be an n by n matrix, so it's a square matrix. The minor m sub ij of A sub ij is the n minus 1 by n minus 1 matrix obtained by deleting the ith row and jth column of matrix A. So what you're going to do, this A sub ij, remember that is one of the entries in the matrix. You're going to go through and literally you can go and block out the row and column that this element is in and write the remaining entries as a single matrix. That will be the minor of that element. The cofactor of that entry, of the ijth entry, is given by C sub ij equals -1 to the I plus j power times that minor. In other words, what's going to happen here, that cofactor is either going to be the minor itself or the opposite of the minor. And really, it's just going to be what happens when I add I and j together. If I plus j is an even number, then the cofactor is going to equal the minor. If the I plus j is an odd number, then the cofactor is going to be -1 times the minor. So let's take a look at an example here. In this case, I know I'm looking at A12. A12 is, remember, it's first row, second column. That is that 3. Now, there is a minor associated with that 3. If you go block off the row that the 3 is in and the column, the row and the column, you'll get in this case, we start with a 3 by 3, so you'll have a 2 by 2 matrix, and that is going to be the minor, and that minor is 4, 9, 7, 8. And then the cofactor in this one is 1 plus 2 is 3, so it's going to be -1 times that minor, which is 4, 7, 9, 8. That's how we go through and work with that minor and the cofactor. Okay, because it's negative, and remember, it's 1 plus 2 is 3, so that's why we ended up -1 to the third power would still be -1, so we have a -1 there. Now we're going to take a look at going and generalize how we can find the determinant of an n by n matrix. And we're going to do it by expanding by a row or column. And the nice thing is you can choose whichever row or column you want to expand by. So what I have here is right here is A is an n by n matrix. And so I'm going to expand by a row or column. In this case, I'm choosing to expand by the row, the first row, and then I'll also expand by the third column. So when I expand by the first row, what I'm going to do is I'm going to take each term of the first row, each element of that first row, and I'm going to multiply it by its cofactor. I'm just going to add all those together. So it's going to be A11 times its cofactor plus A12 times its cofactor plus A13 times its cofactor, and so forth, all the way to A1n times its cofactor. Now remember, the cofactor is either going to be a positive or negative. And the nice thing about these things, these are going to alternate. So C11 here is going to be a positive, so C12 will be a negative, 13 will be positive, 14 would be negative, and so forth. Now, we can also work with the column. So I can expand by the column. So in this case, I'm expanding by the third column. So the determinant of A would also be A13 times its cofactor plus A23 times its cofactor plus A33 times its cofactor, and so forth, all the way down to AN3 times its cofactor. And again, the same thing is true. A13 is 4, that's even, so the cofactor is going to be positive, and so A23 in this case, that's going to be odd, so that's negative, and then positive, and it's going to alternate like that. And as you do your expansions, you will always see that the cofactor is going to alternate between those signs, okay, either positive or negative. And that can have an effect when you end up taking the determinant, because remember, the determinant can be a positive number. It could also be a negative number too. So you got to be aware of all those signs as you're working and as you're doing your expansion. I always will go and write that whole expansion out and then take the calculate that the determinant there. Remember, your cofactor is a determinant of a matrix as well. So the bigger the matrix, you can start seeing that this can get pretty complicated as you're working with this. So let's take a look at an example. In this case, what I want to do is I want to find the determinant of this 3 by 3 matrix. So this right here, the determinant here, again, I can expand by whatever I want to do. And so I'm going to, at this point, expand by the first row. Well, the first row, so it's going to be 1 times its cofactor. Well, that's going to be, it's the first one is 1, 1, so it's going to be a positive cofactor. And that cofactor is just going to be the determinant of this 2 by 2 matrix here, which is 1 times 0, 0, 3, 2. And then the next one is going to be a negative cofactor, so it's going to be minus negative 2 times its minor, which is going to be the matrix, the determinant of negative 1, 3, negative 4, 2. So that's how we got this. And then it's going to be, it was positive, negative, then positive 1 times the determinant of its cofactor is going to be negative 1, 0, negative 4, 0. So you're taking the determinant of those. Well, so this, in this case right here, I want to take the determinant of that. Well, that's going to be 0 times 2 minus 0 times 3. So this is going to be 1 times 0 minus 0. Minus a negative 2 is plus 2 times negative 2 minus a negative 12. So I have that. And then 1 times negative 1 times 0 is 0, minus negative 4 times 0 is 0. So I get 0 there. So when I do the calculations, that is 1 times 0 is 0. That's going to be 2 times 10. And then this is going to be 1 times 0. And so the result here is that's 2 times 10, which is 20. So the determinant of this particular matrix, of our matrix here, is 20. Now, keep in mind, I can choose to go and work with this thing. And now I take a look at this, and I thought to myself when I looked at it, I see zeros in this matrix. And zeros are wonderful things to work with, because when I expand by with the minors, the determinant, this 0 is going to be multiplying the determinant for that cofactor. So it's going to end up being 0 itself. So if I expand here by the second column, in this case, it makes my life easier. It's going to be negative 2 times, and it is negative 1 to the 1 plus 2, so that would make that a negative 1, times, cross off the row and column negative 2 is in, and I get the matrix negative 1, 3, negative 4, 2. And then each one of these, when I expand, it's going to be 0, so it's 0 times that. That's going to end up being 0, and 0 times that is also going to be 0. And so when I do this calculation, that becomes, this part here becomes 2 times negative 2 plus 12, which comes out to be 10, so I still get 20. It doesn't matter which row or column I go and expand by, I will always get the exact same determinant. So if I see a row or column that has some zeros in it, that a lot of times is a good one to choose to expand by, because you have fewer calculations, and then the problem, it generally tends to be easier. Now let's take a look at Cramer's Rule. Cramer's Rule is a way that we can go through and solve a system of equations. And you've seen so far, you've seen 3 different ways to solve a system of, 2 different ways to solve a system of equations. I'm going to throw in a third one with this. The first way was to take it, put it into an augmented matrix, put that matrix into reduced row echelon form, and I could read the solution off. That way allowed us to determine if we did have no solution or if we did have many solutions. And that was the advantage to using the reduced row echelon form. The second way we had was what we did in 8.4, where we did the multiplication and finding the inverse, multiplying both sides by the inverse. Was much easier to go through. It was much easier to work with your calculator with that. And it's a little bit less complicated in terms of going through and doing some of the calculations, because you're not necessarily having to do all that. Then we have Cramer's Rule. Now, Cramer's Rule basically uses determinants of a matrix to go through and calculate the solution, find that solution. And really where it comes from is right here when we're taking a look at a system of equations. We have one equation is a1x plus b1y plus equals c1. And then we have another one, a2x plus b2y equals c2. And what we're going to do is we want to go through and solve this thing, solve this system, and we're going to choose to solve it by elimination. And so, yeah, you're going to see some letters. We're going to eliminate the y. That means I'm going to do that by multiplying the top equation by b2 and the bottom equation by negative b1. So when I multiply the top equation by b2, I get this right here. And when I multiply this equation here by negative b1, I get this. Now keep in mind, you're going to see the order of the letters switch. That's okay because we're dealing with multiplication. Multiplication numbers, 2 times 3, 3 times 2, it's all the same. So when I go through and combine these, the b2a1x minus b1a2x is going to be a1b2x minus b1a2x equals, this part drops off, equals c1b2 minus c2b1. And when you take a look at that, you'll notice, well, in this case right here, we're going to pull that factor of x out. So I have a1b2 minus b1a2 times x equals c1c2 minus c2b1. And if you look at that, these two kind of resemble the determinant of a matrix. And so a1b2 minus b1a2 is the determinant of this matrix here, AD minus BC. A is A1 in the D spot is B2 minus B1 is in the B spot and A2 is in the C spot. So I get that matrix there, the determinant of that matrix times X equals this right here is the determinant of C1, B1, C2, B2. That matrix. And so X then is equal to C1, the determinant of C1, B1 over C2, B2, all divided by the determinant of A1, B1, A2, B2. That's X. The same thing can be done for Y. Okay, so that's really what Cramer's rule is. You're gonna have to go through and determine these two matrices. And once you know how to determine those matrices, life is gonna be good and you're gonna be able to solve these systems. So here we go. Here's Cramer's rule. For a system of linear equations given here, we're going to let there be three matrices, D, D sub x, D sub y. D is just the coefficient matrix of the system. Just taking the coefficients themselves, put them in there. Now you'll notice D sub x, look at what we've done. We've replaced the coefficients on x with the solution. So D sub x, I just take the solution matrix, replace the A's with those solutions, the C's. And there's D sub x. And in D sub y, that's what we do there. We just, again, replace the coefficients on y with the solution. So that's really what's happening. That's how you identify those matrices. And you just take the determinant of those, and that's going to be what we're going to have. So as long as, if this thing right here, as long as D does not equal 0, then I know there's a solution. And that solution, x is going to be D sub x over D, and y is going to be D sub y over D. As long as D does not equal 0. Now, if D equals 0, okay, clearly you'll notice that we would end up with a division by 0 if we tried to do this. So in that situation, there's no solution or an infinite number of solutions. We're not able to determine which. Still, our only way to determine if we have an infinite number of solutions and to come up with a form of those solutions is through putting the matrix into reduced row echelon form. Let's take a look at an example on how to use Cramer's rule. So here we are with Cramer's rule. We want to solve this system. So what I'd like you to do right now is I want you to pause the video and I want you to determine the matrix that's going to give us D. So, write a determinant notation and then calculate the actual value of D and do the same thing for D sub x and D sub y. Once you have those done, come back, we'll take a look at what you did, and we'll finish up this problem. So go ahead, pause the video, see you in a little bit. Okay, welcome back. Let's take a look at how you did. In terms of this, I haven't gone through and calculated the determinant yet. We will in a second. But for matrix D, remember D is just the coefficient matrix. So it's going to be 5, 4, negative 3, negative 2. D sub x is going to be where I take your solution and replace the first column of matrix D with your solution. So I get 1, 4, negative 3, negative 2. And D sub y is where I replace the y, the second column in D, with that solution. And so what would be the coefficients on y? And so I have D sub y as a determinant of the matrix 5, 1, negative 3, negative 3. And so in this case, D is going to come out to be, when I do that calculation, it's going to be 5 times negative 2 is negative 10 minus negative 3 times 4 is a negative 12. So that determinant comes out to be 2. D sub x is going to be negative 2. 1 times negative 2 minus negative 3 times 4 is negative 12, which that's going to be negative 2 plus 12, which will be 10. And then D sub y is going to be 5 times negative 3 is negative 15. And minus a negative 3 times 1 is a negative 3. And so that's negative 15 plus 3, which will be negative 12. And so what we know on this one, what Cramer's rule tells me, is that x is going to equal dx over d, which in this case is 10 over 2, which equals 5. And y is going to be dy over d, which is negative 12 over 2, which is negative 6. So our solution, the solution to this system, is the point 5, negative 6. And you can go ahead, plug in, check that yourself. If you put 5, negative 6, I'll do it in the first one. 5 times 5 is 25, plus our plus 4 times negative 6 is negative 24. 25 minus 24 is equal to 1, so that works. You can check the other one. So this right here does conclude our video on going through and determinants, calculating the determinant, and Cramer's rule. So we'll take a look in class. We'll take a little bit look at some calculator stuff with this as well. But at this point, you go through, make sure you're comfortable with going through and finding the determinant of a 2 by 2. Make sure you're feeling okay about going and doing an expansion. I will ask you to do an expansion by cofactors, along a row or column of the matrix to calculate the determinant as well. And then you'll be using Cramer's rule too. So with that, I hope everything's going well, and we'll see you in our next class.